Don't try anything you're about to see at home.
No, we're what you call experts.
Well, there's your problem.
In this special series of MythBusters,
Almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and impact. With crazy chemistry,
Oh, my goodness.
far-out physics,
One for the whole family.
and insane explosions.
Everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. This episode, shredding genes and fire-filled scenes.
Fire people!
With 6 myths about ignition and exothermic reactions.
Holy moly, the set's on fire!
We'll investigate grease fires, dog bowl fires, and distressed denim. Then press the button on chemical reactions of dramatic and toilet-busting proportions. We're kicking off with an ignition myth from old Western movies.
A cowboy falls off his horse and gets dragged by it. And the friction that's created actually causes the jeans to catch on fire.
Okay, that has Tori written all over it.
Why does it have me written all over it?
Because, Tori, you're the team member who has the least regard for their own safety. Besides, Carrie's got an injured leg, and Grant's already got dibs on the data-gathering gig.
Well, this should be easy enough. We get a horse, we drag you behind it, and see if your jeans catch on fire.
This should be fun.
For us.
At the Growney Ranch, Tori gets himself kitted up in full-body padding, while Carrie and Grant shoot the breeze with Stockman John.
So how do you get yourself in trouble? I mean, does your foot get caught in the stirrup? Does it get caught in the reins? I mean, how do you get dragged?
The common thing is being caught in the stirrup, and in the old days, being caught in the rope. And the rope would hang on to you long enough, or it would actually close in on you while it was wrapped around the saddle horn and then just drag you off.
Okay, so getting dragged behind a horse is plausible. But what's the scientific theory around how the jeans are supposed to catch fire?
Tori's weight represents a downward force that's pushing the jeans onto the ground. And as the horse drags him along, the friction there is going to build up and hopefully cause the jeans to spontaneously combust.
Sounds like Grant is hoping his co-star goes out in a blaze of glory.
He stretches you out like that.
And John's not horsing around about the risk.
So I'm relatively safe.
No, you're not relatively safe. 1%, the horse is not going to kick you. That's the only thing I'm guaranteeing because you're far enough away from the horse. But I've seen it where the horse gets over the rope and starts drawing you into him and then kicking you. So don't let him get under the rope.
Thanks for your words of encouragement.
You're welcome, because you need all the help you can get.
Comes a time when a cowboy gets to wondering if he might be in a little over his head.
In the shop, they're like, oh, you're gonna get dragged behind a horse. And I'm like, yeah, that sounds fun. But then you get out here and you go, gosh, this seems like a really stupid idea. I'm looking around, and I'm seeing rocks, and I'm seeing horse dung. Not only is it gonna hurt, it's gonna be very, very unpleasant.
But this ain't no time for quitting. The steed set to do the deed is named Pistol.
Pistol looks like he's all ready to go. We've got 20 feet of rope that we've got our cowgirl holding on to. She's gonna ramp up her speed and ride directly that direction.
All right, well, you know what I'm probably gonna do is I'm probably gonna hold on to the rope, start off on my stomach, and then as I'm going, I'll try to flip over to my back so that way I can get as much friction on the back of the pants as possible.
To reduce the hazards, Tori is decked out in top-to-toe denim with a padded safety suit underneath.
Fashion police. Top 10 cardinal rules. Denim on denim, no.
Paramedics are on site. and Pistol will be in the expert hands of cowgirl Neela.
Wow, this rope's a lot shorter than I thought it was gonna be.
To ensure absolute scientific accuracy, Grant takes the temperature of Tori's rear.
We have an infrared surface thermometer, so we'll measure how hot the jeans are before the run, 103.5, and compare that to how hot they are after. And I'll just be carrying this just in case.
Stretched out 25 feet from Pistol's back legs, Tori should be out of kicking range. Let's ride.
Okay, you gotta be on your back.
With dung and rocks flying, Tori contemplates the life choices that led him to this bizarre moment in time.
Oh, hit a patch of dung there.
I was just trying to hold onto the rope. I was hoping that the horse would stop soon. I just kind of kept my eyes closed and my mouth shut.
Tori's cheeks clock up some serious speed.
All right, we're topping out at 20 miles an hour.
And they have to face a final indignity.
Okay, flip over, flip over. Okay, got it.
That was great. Can we do that again?
116 and a half.
Post-run, Tori's posterior temperature has increased by 13 degrees.
Definitely, the friction did add some heat, but I mean, these pants aren't smoking.
Time for a second gallop.
Round 2.
To try and increase the amount of friction, they'll ramp up the speed.
All right, good to go.
Drag that no-good varmint out of town, Pistol. At a quicker pace,
They're going way faster this time.
Tori and the dung are really flying.
Oh my God, they're topping at 30.
I sure hope he doesn't have a date tonight.
This time, we went a little bit faster. A lot faster, it felt like. Felt like I was bouncing around a lot. My head was going all over the place.
When his gluteus maximus finally grinds to a halt, our vigilant data collector rushes in.
It's 145 and a half degrees.
Whoa.
So an increase of 34 degrees.
But still, it didn't catch on fire. And that's kind of what I figured. I figured the jeans were just going to tear away before they caught on fire.
Denim this distressed could be a hit on the catwalk,
Jack.
but fire from friction was fiction.
Tori did experience an increase in temperature of his clothing, but he did not burst into flame. Both the jacket and the jeans are safe for now.
This myth has more holes in it than Tori's jeans. It's busted. From a failed ignition to a myth that is guaranteed to catch a light.
We're doing grease fires.
More specifically, that trying to extinguish a grease fire with a cup of water will cause a 30-foot fireball.
That sounds genuinely tasty. Let's dig in.
Can it really be true that a mere 8 ounces of water poured over a grease blaze will kickstart a 30-foot fireball? Or is it just a flash in the pan? To find out, Adam's kicking off on a high note.
This is just as much fun as it looks. It's also as scary as it looks.
3 stories up, he's setting up their homemade benchmark scale.
This scale right here is 30 feet tall, and the myth says that we're supposed to get a fireball 30 feet tall. This will tell us if that's correct. Personally, it strikes me as a little ambitious.
It does seem like a tall order, but if you're a Mythbuster, that only makes it more appetizing. So what exactly is on the menu?
So what we've got here is a frying pan full of 2 quarts of oil. We got a thermistor to check how hot it's getting. We got 8 ounces of water to dump on it once we catch it on fire. And we got a gauge to tell us if the fireball we get is in fact 30 feet tall.
2 quarts of canola oil and some water, 30 feet fireball, nah.
The man with the mo says no. But for the first of 2 oils, canola, it's flame on.
We're good to go, Adam.
Let's do it.
Step 1 is heat the oil up to horrifying levels. Never, ever do this at home.
515 degrees, and it's only been like 6 minutes. This is nice and fast.
100 Fahrenheit degrees later, canola's flash point is reached. That's the temperature at which it can start to burn.
I saw a little bit of fire. Did you see that? We're past the flash point.
When it gets to 680 degrees Fahrenheit or 360 degrees Celsius, it'll reach a state called auto-ignition, where it's going to burst into flame no matter what.
600 and how much?
645.
Oh, we're close to the auto-ignition point.
And I see flame on it.
All right. I'd say that's a grease fire.
From the view up here, I agree. And the one thing you should never do to a grease fire is add water. But how bad can it really be?
All right, canola oil, putting out a grease fire in my kitchen, perhaps unwisely, in 3, 2, 1. Wow!
Yikes, if I had a mustache, it'd be history.
I was a little surprised at how large the fire was that came off of this. I'm glad we set this thing up remotely, because we would have had a problem if we were doing it right next to the stove, like most people would.
That exceeded all of my expectations. I honestly don't know what to say. I'm kind of gobsmacked by how energetic that was.
Sure, it's an horrific fireball. But before we get too carried away, let's not forget the myth says with 8 ounces of water, it should go 30 feet.
12,
15 feet. Oh my God, 20 feet.
That's still 10 feet or 30% short. The guys aren't done yet, but before we move on, we need an explanation about how water causes such a violent reaction.
Well, that water went from, room temperature to all of a sudden the temperature of the oil, which was around 700 or 800 degrees. That means it turned to steam. Now, when water turns to steam, it expands up to around 1,600 times the volume. That expansion was actually an explosion that exploded upward out of this pan, carrying all this oil along with it. And since everything's so hot, it all just becomes a big fireball.
So never, ever put water on burning oil. Unless, of course, you're a Mythbuster and the fire department is supervising.
Let's do it again.
Next up, it's peanut oil.
So the auto-ignition point of peanut oil is over 200 degrees hotter than the auto-ignition point of canola oil. Will that translate to a more energetic fireball that's even bigger than the last one? I don't know, but my intuition says yes.
With the peanut oil heated to 850 degrees, my fictional mustache is quivering with anticipation.
All right, here we go. This is water poured on a peanut oil fire on your stove in 3, 2, 1. I felt that from here.
Yeah.
Me too.
That was 30 feet, man. I watched it. That was 30 feet.
The peanut oil gave us a nice big ball of fire, and it went up 30 feet. So I guess the myth is true. It's time to go home.
Whoa there, Jamie. Not so fast.
Up she goes.
Are you sure?
5 feet.
Really, really sure
15.
that the actual fireball went up 30 feet?
Yeah, I don't think that's quite 30 feet.
Yeah, the smoke kind of got up that high, but it looks to me like it's maybe 25 at best.
Maybe, yeah.
No 30 feet. I think we got a little more work to do.
I think you're right.
To get a bigger fireball, they're first going to downsize.
We're still in the fire training center, but this time in a fireproof room.
And experiment with throwing more water into the mix.
Well, now we need 1 teaspoon up there.
For a control test, let's see what 8-to-1 oil-to-water ratio does in this smaller scale.
Scale kitchen conflagration. 1 teaspoon of water. Wow!
Yep, it's frightening stuff. Even a tiny amount of water can still cause a kitchen catastrophe.
Last time we did 8-to-1. This time we're going to do 4-to-1, and we'll ramp it up from there.
So will twice the ratio of water shoot the flames twice as high?
I think we're going to get a bigger poof of a fireball. There we go. Here we go. 3, 2, 1. Hard to say if that was bigger. It was at least as big.
But as big is not big enough. They want bigger and better fireballs. So the boys up the water volume again, 2 to 1. Half as much water as oil.
3, 2, 1.
It's getting better, but there's room for one final test. Equal parts oil and water.
Here we go. In 3, 2, 1.
Clearly, there's not much in it, but the guys feel that there is some improvement at the higher ratios.
I don't know, man. It's really close, but if I had to call the ideal ratio of water to oil, I'd say it's either the 2 to 1 or the 1 to 1 ratio.
Yeah, I'd make the same call. But, you know, it is kind of like making the decision as to whether you want to be well done or really well done.
Yeah.
I wouldn't want to be in either of them.
But will that marginal difference make a difference in full scale? Will they finally fire up the mythical 30-foot fireball?
What could be wrong with my cooking?
They're almost ready for the big bang.
Okay, and tip.
That's perfect.
The only thing left to do is erect a 30-foot yardstick, and they can launch their test.
It's really droopy.
I know. It's gonna, well, we can reset.
But even a minor droop can end in embarrassment.
That's what we call a zero property damage oops moment. Luckily, no one's hurt.
Adam performs a droop reversal procedure.
That looks pretty straight to me.
And at last, it's time to see if water plus a grease fire can ever equal a 30-foot fireball. With the small-scale results in mind, they've got a 2 to 1 ratio of ingredients. 2 quarts of oil to 1 quart of water.
There's a pretty stiff wind out here, so I'm reckoning that we're not going to get 30 feet straight up, but we might get 30 feet sideways, and that's what the myth says, 30 feet. It didn't say straight up.
Jamie's happy with horizontal, but Adam's still hoping for height.
I want a 30-foot fireball, a genuine, bona fide, dyed-in-the-wool, homegrown 30-foot fireball.
This is it. The final countdown for the ultimate disaster test. Will the worst-case scenario for a kitchen fireball meet Adam's high hopes?
Okay, yeah?
Yeah, go for it.
That was 30 feet.
That was 30 feet. Nicely done.
It looked good from here, with 2 quarts oil and 1 quart water. That's 4 times the original amount they used. Have they finally cracked it?
It worked.
It works beautifully. That was one 30-foot-high fireball from average amounts of cooking materials and regular old kitchenware.
And the final verdict from the high-speed referee?
There it goes.
Yep.
Yeah,
28, 29, 30.
easily 30. That's a lot of fire out of a little pot of oil.
At last, it's mission accomplished. 8 ounces of water can't give you a 30-foot fireball, but a quart sure can.
It's there.
I will now regard making French fries with the same fear I have for using a table saw. But as far as the 30-foot fireball from 8 ounces of water dumped in oil, it's a no-go. It's busted.
Next up, a Fido-themed flare-up.
All right, family decides to have a picnic out on the patio. They get everything all set up, they go away, they come back, and the patio is totally engulfed in flames. The fire investigators blamed the dog bowl.
Wait. How'd the dog bowl set the fire?
Well, apparently, the dog bowl was able to focus the sun's rays to such a tiny point that it got hot enough to start burning the deck down.
Interesting.
According to the myth, dog bowls can go full pyro on your patio. But did they really ignite this inferno? Or were investigators barking up the wrong tree?
Time for the MythBusters Picnic of Death.
No dogs get hurt during this experiment, right?
Absolutely not. Okay, family decides perfect day for a barbecue. So they get everything all set up. and then they walk away.
Now, we've created a highly flammable set, hoping for a blazing inferno. Now, for that, we've put dog bowls, focusing the sunlight into small areas, hoping to take advantage of really low ignition temperatures, like 130 degrees Celsius for dried flowers, 150 degrees Celsius for decaying wood, 212 degrees for paper. Now, at the end of this experiment, if everything goes perfectly, we should just have a charred pile of nothing here.
And to achieve that, they've got two kinds of dog bowls. The shiny, curved surface of the metal bowl reflects the sunlight into a super hot focal point, while the glass bowl acts like a giant magnifying glass, bending the sunlight into focus.
Ooh, that's a nice beam.
In just a few seconds, the flowers...
There's a burn mark. It's burning. You guys, the flowers are burning.
and the tablecloth start to smoke.
Smell that burn.
But the weather is pooping the pyro party.
The wind is blowing, which is cooling off what we're trying to heat up. So we try to fix that by putting up a wind block, but that's not helping. Another problem we're having is the humidity in the air. Now, it happens to be 30% humidity today. That's not that low. So because of all that moisture in the dead tinder, it's absorbing a lot of the energy from the sun. So if we're expecting to see this area catch on fire, it's not gonna happen today.
Not unless they turn up the heat. But what do you use to create an instant summer?
One of these. It's a theatrical light we call a 20K. Puts out roughly 20,000 watts of power. But for our purposes, it's ideal because this tungsten filament puts out 80% of its energy in the form of infrared heat. And for us, that's gonna heat up our set and it's gonna reduce our humidity. You guys ready to turn up the heat?
And action.
Remember, they're still using the sun to create the focal points.
Ooh, that's a good one.
But the movie light is creating a hot set on a cold day.
Ooh, it's hot in here. It's like Palm Springs weather.
With the temperature on set peaking at 105 degrees, the focal points heat up fast.
Temperature's clearly climbing in this picnic here. The metal dog bowls are making hot points. The glass dog bowls are making hot points. I think this thing's going up soon.
Oh, we got a fire. Holy moly. The set's on fire. The set's on fire.
After just 2 minutes baking under the sun, they have ignition.
Try again. Not in my face. There we go.
And despite Carrie's best efforts, the glass bowls are starting more fires than she can put out.
Yeah, that's how you get a piñata. Fire!
We got fire, people!
Incredibly, after just 5 minutes, the glass bowls have lived up to their fire-starting reputation.
So can a glass bowl create enough heat to start a fire? You bet it can. But we had to manipulate the circumstances. It's a very specific set of things have to come together. You have to have low humidity, high ambient temperature. The sun has to be in the right place in the sky. But if you have all these things, yes, you can get a fire, and this one's confirmed.
Well, that was one heck of a family barbecue.
I call that confirmed.
Totally confirmed.
Get the dogs.
All right, come on.
I love dogs.
Now we're leaving ignition myths behind in favor of fiery conflagrations of a more chemical kind. Exothermic reactions are chemical reactions that produce heat. And we're kicking off with a couple of weird ones.
What are they?
Elephant toothpaste and exploding snakes.
Elephants and exploding things. Are we sure that this is something that people can do at home?
We'll be finding out with adult supervision if you try at home. First up, elephant toothpaste, which uses household ingredients.
All you need is a little hydrogen peroxide, the kind you would get for dyeing your hair, liquid dish soap, a little food coloring for pizzazz.
Ooh.
And finally, the catalyst, which is plain old yeast.
Are you about to blow our minds?
I am. Stand back. Whoa!
Whoa.
It's like a volcano from science fair.
Look at that.
It's minty fresh.
It's easy to see why this supersized foam is called elephant toothpaste.
Now, in its basic form, hydrogen peroxide is extremely stable. But what's happening here is when you add the yeast, it's decomposing the hydrogen peroxide very rapidly and releasing oxygen. The oxygen is getting captured inside the liquid dish soap, which is creating bubbles in this big, foamy, awesome mess.
And although it passes the try this at home test, it's just a frothy fountain. So how about an only on MythBusters twist?
Don't try this at home.
All right, to take this experiment from go ahead, try it at home, to MythBusters danger, we're gonna use some lab-grade components here. We have a higher concentration of hydrogen peroxide, and for our catalyst, potassium iodide. Now, these are much more caustic chemicals here, and the reaction is a lot more energetic.
Okay, so take two, but this is definitely a do not try at home.
One step back.
Is it gonna get crazy?
Yeah?
You about to drop some science on us?
You ready?
Yeah.
Do it.
Whoa! Oh! What the?
Much more energetic
Oh my
experiment.
God. Look how hot it is.
Yeah.
See the steam coming on.
Yep, enough toothpaste to bring a shine to even the most tarnished tusk.
There you have it. 2 versions of elephant toothpaste. The first, definitely a try-it-at-home experiment. It's just household items like peroxide and yeast give you this beautiful fountain of magical foam. The second, a little more dangerous. We're talking about lab-grade ingredients creating an exothermic reaction with a lot more oxygen, a lot more heat, and a much more spectacular mess. Definitely worth the cleanup.
But I still don't understand why they call it elephant toothpaste. I wasn't aware that elephants brush their teeth.
But now we've seen the toothpaste, didn't someone mention an exploding snake?
Now, for the most part, elephant toothpaste is the sort of experiment you can do at home. This next one is a little bit different. It's called explosive snake. Now, the first part of it involves sugar, which by itself is innocuous. The part that makes it different is the other half, sulfuric acid. It's corrosive, caustic, and if you splash on your skin, you could get severe burns. So, unfortunately, not the sort of thing you want to try at home. And to do this experiment, I think I'm gonna need a slightly different wardrobe. Ah, that's better. So, I've got an apron to protect my clothing, acid gloves to protect my hands, and a face shield for my face. Now it's time to mix up the elements.
It's another do not try this at home. But will it be explosive?
It's coming. Okay, so what happened here? Well, the acid interacts with the sugar and breaks it down into its components. It releases water in the form of steam and leaves behind carbon, which is what the snake is. Now, it's a very cool reaction, but not necessarily all that explosive. I think in order to be explosive, it should be faster and more violent. And I think I can find a reaction that does that.
So Lab Raider Imahara swaps out the sugar for a classified organic compound, adds the sulfuric acid, then brings a little heat to the equation. But will this result in that explosive snake?
Watch it. Okay, don't blink. This is gonna happen really fast. Okay, this is it. Go away! That's amazing.
It's an instantaneous process called deaminization. The sulfuric acid dehydrated the compound, leaving in its wake a flaky carbon snake.
So conclusion, 2 explosive snakes by different means, but unfortunately, because of the sulfuric acid, you can't try either of them at home.
So while the basic elephant toothpaste is okay to try at home with adult supervision, but the other extreme experiments you've seen are definitely not recommended. Next, can sodium react so violently with water that it blows a hole in a brick wall? It's a myth that comes from the 1980s action show MacGyver. To test it, they'll start by positioning a see-through lab, where they'll be able to gauge the explosive properties of sodium in small scale. With a pulley, a weight,
Yeah, perfect.
a bowl of water, and a glass vial of metal sodium, Adam hopes to test the potential without bringing the house down. Sodium is an alkali metal, which makes it likely to create an exothermic reaction when added to water.
I'll cut that string, break the glass that the sodium's in, release it into the water, and show us what happens. All right.
Pure sodium is so volatile, it could even react with moisture in the air. So, better safe than singed.
That's why I am so well protected from any kind of splashback, toxicity, anything. Nothing can get inside my suit, and with the face shield on, I think I'm properly protected.
Giant banana number 2 reduces the risk by painting the tray with mineral oil. This gasoline byproduct stops alkali metals from reacting with atmospheric water.
Kind of like a cooking show, except it'll kill you.
Okay, so now it's sitting on the mineral oil. Everyone eyes open, this is for real. It's scary.
The sodium metal cuts just like butter.
Look at that.
Whoa.
That is far out.
So that, oh my gosh.
All right, so
That's just metal.
2 small slices make 1 thin ground, and that's exactly what MacGyver used to blow a hole in a wall.
1 gram of sodium. It looks so innocuous. It's part of table salt, for crying out loud.
Good luck.
I'll see you at the shield.
Be careful.
Hey, Adam's middle name is Careful. Then again, his last name is Savage, so anything could happen. They'll do this test twice. First, with the vial sitting on top of the water.
So this is sodium surface test in 3, 2, 1.
Wah, wah.
No, it's gonna take a second.
There you go.
That was cool.
But it wasn't a huge bang, yet. Time for test 2, this time immersed in water.
From what I understand from the science, being under the water is probably gonna be less of a reaction than being on top of the water.
Interesting. Yeah. All right, let's find out.
This is sodium underwater. In 3, 2, 1. That looks like it worked.
Yeah. Whoa! Well, that was a bigger one.
Yeah.
You have to wonder if Adam ever gets tired of being wrong. That was definitely a bigger blow-up. And that's a good enough result for Jamie to call in the contractors.
Okay, you guys are gonna build a wall. We're gonna blow it up, but do a good job anyway. Let's go.
The scenery goes up fast, and if all goes to plan, it'll be coming down even faster. Today, the part of MacGyver will be played by Buster, once Jamie's made him decent. But pants don't always make the man. In this case, it's all about the hair.
It looks a little like you.
Okay. Now, he buried the jar in the sand, right?
Yeah, but he kind of like, he did this, and then he did this.
Okay.
That kind of thing. So we just need a couple more bags that are cut open to make this look kind of good. Yeah.
They've replicated the MacGyver scene as best they can, but Adam's added a magnet to the trigger, so the boys can be sure they're safe behind the blast screen.
I put a little tiny bit of metal that will be in this pill in addition to the sodium. It's actually ferrous, which means it will be magnetized. I'll prep the sodium like this. I'll fill the bottle with water. When we're just about ready to go, I will carefully, ever so carefully, screw this down on top, retreat to behind the safety shield.
Then pull the magnet off the screw cap, dropping the pill in the water, and hopefully proving you can trust everything you see on TV.
In 3, 2, 1.
They huddle behind the blast shield, waiting for the gel cap to dissolve so that the sodium hits the H2O.
In less than a minute, we should see something. 50 seconds. Should happen any second now. Isn't it always like this? 110.
So what are we gonna do if it doesn't blow up?
I say we, wait the requisite 20 minutes and then approach it very cautiously.
After half an hour, there's nothing doing.
Try not to break your arm here.
So Jamie rents out the latest in this season's line of bomb suits.
Feel like I'm ready to go out clubbing.
Complete complete with this season's must-have accessory, a tiny broom.
It's not dissimilar from how Jamie was dressed when he first came to Earth.
Odds are the reaction has occurred, but wasn't strong enough to break the bottle. But there's always a chance that the reaction has been delayed. Hence the tiny broom and the tentative poke. If it's safe, Jamie should give us a signal. Bingo!
Well, it certainly looks like some reaction has happened, and I don't see any sodium, and we put it in there, so the reaction happened without breaking the bottle.
It seems exothermic reactions can be a little deceiving.
We saw a reaction in the lab, and it looks good, but a lot of times a little smoke, a little pop, or a little poof is, you know, it's more bark than bite.
Unfortunately for MacGyver, it doesn't seem to work in real life like it did in the show.
So 1 gram of pure sodium won't blow a hole through a brick wall. But on MythBusters, there's always the option to go big before they go home.
So what are we doing?
Well, we're gonna try and blow another hole in the wall, except I'm gonna use a lot more sodium and a much bigger pill.
What, is that for a horse?
It is, in fact, for a horse.
Adam packs his horse pill with 100 grams of sodium metal.
It's a lot of sodium.
That's 100 times more than MacGyver used.
It's a dangerous amount of sodium to put in water. So I'm expecting big things from this.
Aren't we all? And
2, 1. Oh, I hate this. Nothing's happening.
4.5 minutes later, the pill finally pops.
The point of failure was, of course, the weakest. Whoa!
2 explosions. Still barely enough to uncap the bottle.
Look, that's what's left of the gelatin capsule. That was an explosion, but this is not a high explosive.
Luckily, Adam's got an idea to test a different alkali metal.
And our plan is to introduce potassium, which is far more reactive than sodium, into water in a metal pipe. Boom!
When we did the thing with the sodium, we used a chunk about the size of my thumb. This time we're going to be using a bunch of potassium, about this much.
The metal pipe is sealed at the back, and it's got a lip up here. It's going to hold water up to this line. In the back here will be 2 jars, each glass, each filled with 250 grams of potassium. Up here in these pipes will be a weight. There'll be a pin here which will pull from behind the blast shield, dropping the weight onto the bottle, breaking it, releasing the potassium into the water, and directing all the energy out the front through our wall, hopefully.
That's 500 grams of pure potassium. The original myth was 1 gram of less reactive sodium.
Now he's pushing the mortar up against the wall so that the only place the energy can go is right at that wall.
Will potassium bring the smashium?
This is for love, money, and science. 500 grams of potassium. 3, 2, 1. Wow!
Well, that didn't make us wait.
A smoking show. But where's the rubble?
MacGyver, my brother, my compadre. We have to take him down on this one.
We've sidestepped this result for far too long. But Jamie and Adam still have a wall to bring down.
We came here to get a hole in the wall, and darn it, we're going to get a hole in the wall. When in doubt, C4.
The great thing about working with JD is that when we said we want a hole in the wall, all he says is, how big?
Of all the letter and numeral combinations in existence, C4 is the one guaranteed to bring most satisfaction.
1.
Oh, that whole wall went away.
I think the wall might be gone.
Sorry about that.
That's what I call an exothermic reaction. But MacGyver is still sitting pretty.
It knocked MacGyver's mullet right off his head.
But not the stash.
It's pretty definitive what it takes to get through a wall. And the alkali metals just ain't it.
So, how did MacGyver do?
Well, I'll tell you what I love about him is that his basic premise that alkali metals are reactive with water is sound.
Yeah, but the idea that you can use them to blow a hole in the wall, totally busted.
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 From sodium and potassium to some alkali metals that are a little more spicy.
There's this internet video floating around where these guys throw cesium rubidium into a bathtub and they liken the explosion to a hand grenade. Fans want to know if that's actually true.
Okay, that's cool. But instead of bathtubs, why don't we do toilets?
Genius. Because, let's face it, toilets are a lot funnier than bathtubs. Ask any 6-year-old or any MythBuster.
What are we blowing up today? Toilets, bathtubs.
Everything but the kitchen sink.
They'll be attempting to create a hand grenade-sized explosion using 2 alkali metals, different to the ones Adam and Jamie deployed.
Anybody got anything to read?
But before they get to the unusual elements, rubidium and cesium, they need a control test.
Now, on the internet video, they said that the reaction was equal to a hand grenade explosion. Just got to clean out the pipes. So we need to see what that looks like in order to have something to compare with. How great is this? We get to start off with a bang. We're gonna blow the crap out of that toilet. Get it?
Fantastic. And we'll plumb even deeper depths of toilet humor after Grant releases this explosive little nugget.
This is a grenade, but it's not a live grenade. In a live grenade, you'd have TNT in here, you pull the pin, the clip pops off, and this is what would set off the explosion. But what we're gonna do today is fill this with enough C4 to have the equivalent blasting power of the TNT. Then we're gonna set it off with a blasting cap. That way we can control exactly when it goes off, and it will be much, much safer.
All right, well, we have an actual grenade wired, and it's sitting in the toilet, ready to blow.
And once we see that explode, we'll have something to compare the alkali metals to.
Okay.
Let's blow this thing up.
Fire in the bowl.
3, 2, 1.
Oh! The toilet's gone.
Someone fetch the mop and bucket.
Oh, we blowed it up real good.
That's nice.
All that's left is the water tank.
God, the bowl just shattered.
Yeah. We destroyed this toilet, and now I know what a real grenade looks like when it goes off.
So now we've got a great reference for what it should look like when we put our alkali metals in a toilet, in water.
I just don't think that the alkali metals are gonna have this kind of reaction, but I hope I'm wrong.
But we all know toilets can churn out a surprise or two, so anything could happen, especially when we throw in rubidium and cesium.
This is cesium, and this is rubidium. And they're part of a special class of elements called alkali metals. Now, what makes them special is they have 1 electron. Now, normally, what they want to do is react with other things and give up that electron. Now, what happens when the alkali metals react with water is they release a lot of heat, and the other byproduct is hydrogen gas. And the heat tends to ignite the hydrogen gas. It's a perfect storm of something that causes an explosion.
But how exactly are they going to safely introduce these evil twins into the water?
Pretty simple. It's a little guillotine. Weight drops down onto small glass vials, which are holding the metals, releasing it into the toilet, and we'll see what happens.
Now, normally Grant's a better shot when he's using the toilet, but what he's doing right now is he's wetting down the ground, so in case there's any excess alkali metals that fly out of the toilet, they'll hit the water on the ground and react, so we're not leaving any of the metals behind.
First metal set for release, rubidium.
Rubidium fun fact. This stuff, rubidium compounds, are put in fireworks to make the color purple.
In the video, they said they used 2 grams, and they got an explosion the size of a hand grenade. Now, we're gonna use 25 grams. That's more than 10 times the amount. So if it's true what they're saying, we're gonna have a huge explosion.
You'll be the mayor of Rubidium Town. Ready?
Yep.
3, 2, 1.
Whoa!
That was quick!
Look at that cloud.
It was a perfect release. The string was cut and the guillotine fell. The rubidium was released into the water. And cue the chemistry. The sudden release of hydrogen gas and heat combines to give us a refreshing toilet bowl geyser. Rubidium could make a great toilet bowl cleanser. But hand grenade? Not so much.
So the chemistry predicts a big reaction. I guess it's a big reaction on a chemical scale, but not on a grenade scale. We got a huge cloud and a little spark, a little flash, but no explosion, no shattering of the toilet bowl. So rubidium doesn't do it.
Well, we may not have had hand grenades, but at least we still have good chemistry.
But it's not over yet. An explosive number 2 beckons. And when the moment seizes you, seize the cesium.
This is the most reactive alkali metal that we can get our hands on that's not radioactive. We're gonna put this in the toilet bowl and see if it behaves when exposed to water like a grenade.
Okay. In 3, 2, 1.
Cool.
There was a little bit more reaction, more popping, but it was just a big cloud of gas again.
A gas cloud that leaves the team deflated.
Now, I feel like I've been lied to because what I saw on that internet video was an explosion. What I saw here was a cloud of smoke. Now, a cloud of smoke is not gonna destroy a toilet like a hand grenade will.
Leading to the earth-shattering realization that sometimes things on the internet aren't totally true.
Which means they faked it, and this is busted.